Side? Side, you may have to, yeah, I was going to say you may have to unmute your microphone. They've set up GoToMeeting so that everybody that logs in is muted automatically, and I can't get them to change it, so you just got to remember to unmute that mic when you first log in.
Okay.
So how's calculus going?
Good. Today we took our quiz on like the first and second derivative, then we'd have to draw a graph using that.
Okay. So you did good?
Yeah.
Okay. What's up next? Or what's next?
She didn't really tell us.
We are using the same book. Is she pretty much going by the book?
She doesn't really use the book, so.
Okay. Do you have any material you can send me a picture of? Has she given you any indication of whatsoever of?
No, we just took our quiz today, and then she said we'll get started on a new lesson on Monday. Actually, I think we're not going to do anything on Monday and Tuesday. Well, Tuesday we don't have anything going on. On Monday, I think we're just going to have an off day, kind of. Just watching
Thanksgiving? Thanksgiving next week?
Yeah.
Okay. So it sounds like you have not gotten into integration at all.
No.
But you've covered differentiation, all four rules, including the chain rule, including implicit differentiation.
Yeah.
Including related rates.
Yeah.
Including optimization.
I don't think we've done that.
Let's do some optimization. These are kind of fun. And you'll definitely do that. Let's take the classic optimization problem. If I have a piece of cardboard that is 10 by 8, doesn't matter what its dimensions are, but I'm going to make an open-topped box by cutting out 4 corners and folding up the sides. Got it?
Yeah.
Okay. And I'm going to call this X, that dimension, same as that. In other words, I'm cutting out squares. And then I'm going to fold up this side along that dotted line. And I'm going to have a dotted line here, here, and here. So I'm going to end up with a box whose base is basically that amount right there. You see how that's going to work?
Yeah.
Okay. And it won't have a top on it. In other words, you could do this. You could take a piece of paper, a rectangular piece of paper, cut out square corners, fold it up, and you'll have a box. Okay? Now, the question becomes, what dimension do I make X so that the volume of the box is as big as it can be? Notice that if I made X 0, I would have no volume. Right? Wouldn't have any sides to my box. I would still just have a flat piece of cardboard.
Yeah.
If I make X 4, then it folds up like a suitcase and I still have no box. So X has to be somewhere between 0 and 4. For me to even have a box. What is the formula for the volume of my box? What's the standard formula for the volume of a box?
Base times height times width.
Yeah, the 3 dimensions of that rectangle are going to be my volume of any rectangular brick. It doesn't matter if it's a cube, then it's base times height times width, and they're all the same. But if it's a box, that's a rectangular box, then it's whatever my 3 dimensions are. Well, let's put that in terms of x. What is my base?
Um, 10 minus 2x.
What is my width of the box going to be?
8 minus 2x.
And what is the height of the box going to be?
2x.
The only thing that gets folded up is this part right there.
Okay, so
That's x.
okay.
So the height of the box is going to be x. You see that?
Yeah.
Okay, so there's my volume equation. Volume is equal to that. So, and volume is a function of x. So what do I know about calculus? I know that if I take the first derivative of this function and set it equal to 0, I will know where the maximum volume is. In other words, if I plot this function, if I graph it, it's going to look something like this, okay? I want to know where this point comes right here. What value of x produces a maximum? That'll be the volume, that'll be the biggest volume box I can make if I can solve for x. Well, first step, let's multiply that out. Before we can take the first derivative of it, let's multiply it out.
Okay,
Easiest way to do this is to multiply that by that, and then take your answer and multiply it by x.
okay, so 4x squared minus 36x plus 80.
And then multiplying all of that by x makes this an x, makes this x squared, makes this x cubed. With me?
Yeah.
So that's my volume of my box. Whatever x is, that's going to be the volume of it. Okay? Now, if I take the first derivative of this function, v prime of x, what is that equal to?
12x squared minus 72x plus 80.
Now, I know that the graph that I drew, not quite the way I drew it. What do I know about the first derivative at that point right there?
That's the relative, or
What's the slope of the tangent line at that little local maximum?
0.
Yes, that's the key. That is one of the most fundamental principles of calculus, is if you can take the first derivative of a function, set it equal to 0, you locate all of the spots on the function that have flat tangent lines. Well, that's one of them. That's another one. Notice that we're looking at a quadratic. We're going to get 2 solutions. Well, one of them is going to be this maximum. The other is going to be that minimum. Okay? Now, the way we're getting it is to factor. In other words, I'm going to set that equal to 0. And then I'm going to factor this thing. Can I take out, I can take out a 4, that'll help. And then I can divide both sides by 4, that'll help. Now at least I have an easier quadratic to factor. Let's see if anything easy works here. It's 3x minus something times x minus something else. In other words, I know it's two minuses. That's the only way I can produce a plus. And let's see, how am I going to get 5 and 4? So close. What else multiplies to 20? 10 and 2, also so close. In other words, that gives me 16x in the middle, minus 16x. 5 and 4 gives me minus 17x in the middle. 4 and 5 gives me minus 19x in the middle. I can't seem to factor that. What are other factors of 20 besides 4, 5, 10, and 2? That's it. So I got to use the quadratic on this. Remember the quadratic?
Yeah, negative b.
Go ahead, as long as you remember it, go ahead and substitute the proper numbers for it. In other words, I trust that you know the general formula. So now what's the specific? In other words, let's plug in A, B, and C and see what we get for x. What's minus B?
18.
Oh, I see what happened here. I made up these numbers for my piece of cardboard, and that's why nothing's coming out smooth. But that's okay. 4 times A, which is 3, times B, which is, or C, which is 20, all over 6. Okay? Now, let's see. That's 240. 18 squared is going to be more than 240. So we do have a positive answer. Let's see. I can do this. Let's see. X is going to equal 18 plus or minus, what's 18 squared? Hold on. 324. So we have the square root of 324 minus 240 all over 6. It's not going to be too bad. 18 plus or minus the square root of 84 all over 6. 84 is divisible by 2, or rather 4, so I can factor out a 2, and what's left? 21 all over 6. Finally, I can divide top and bottom by 2 to get 9 plus or minus root 21 over 3. And root 21 doesn't simplify. So the dimension I want on my box is basically one of these is a maximum and the other one's going to be a minimum. Well, yeah, this is equal to 9 plus or minus root 21 has to be what? 4.5 maybe? I'll approximate it. So I have two values. I have 9 plus 4.5 divided by 3, and I have 9 minus 4.5 divided by 3. Well, 9 plus 4 and change divided by 3 is 4.5, I believe. Yeah.
Yeah.
And 9 minus 4.5 divided by 3 is 1.5. So those are my two values of x where my tangent line is horizontal. Okay? Which means I probably drew my function slightly wrong. My function looks like it probably needed to be something like that, where my minimum comes at x equal 1.5 and my maximum comes at x equal 4.5. What's the problem? Which of these answers is not possible? First of all, remember what my restrictions on the box were. I can't have x being greater than 4. Because if I have x being greater than 4, I won't have a box. I won't be able to fold it up into a box. So of these two solutions, I can throw out this one, and this is my proper solution. When x is 1.5, approximately, I will have a box that has the biggest volume it could have. Now, what is that volume? Well, I need to go back to my volume equation. In other words, what is V of 1.5? You plug it back into the original equation. Is all I have determined is what value of x produces a 0 first derivative. In other words, I took the first derivative, set it equal to 0, solved for x, eliminated the possibilities that weren't possible, like 4.5, and ended up with the value that's going to produce my maximum. And that's all I have to do is figure out what v of 1.5 is, substitute 1.5 for x, multiply and add it out, and you get what the volume of the box is. But notice I did not get an answer. In other words, my 1.5 was rounded off. Remember, I had square root of 21 that I called 4.5. So my answer is an irrational number. It's like 1.397. In other words, it's not a number that you ever could have come up with on your own without calculus. And it was a function that was a cubic. Had our function been a quadratic, well, you know how to figure out quadratics maximums or minimums without calculus. Just their parabolas, and it's wherever the bottom of the parabola is or the top of the parabola. That's where the minimums and maximums you're going to find them. So for quadratics, we don't technically need calculus, although it works. In other words, had this been a quadratic, we still could have taken the first derivative, set it equal to 0, and come up with our answer, but we wouldn't have needed calculus. With cubics, we don't really have any way of figuring out where the maximum of that occurs in our domain, 0 to 4. The only way we have of doing it is by taking the first derivative and setting it equal to 0. Now, there's another classic optimization problem that's a little different and involves two equations. And this problem is you have a farmer who has a barn and he wants to build a corral in a rectangular shape or a square shape, whatever, off the side of his barn. And he has a certain amount of wood. He has 2,000 feet of wood. Guess I don't need that if I wrote FT, huh? Okay? So we know he has 2,000 feet of wood, and we want to know what dimensions to make this corral to give his animals the greatest possible area. Another calculus optimization problem. The very first thing you need to do when you're doing optimization problems is figure out what the formula of what you're trying to optimize is. Well, what are we trying to optimize here? Trying to optimize area, right? What's area equal to?
Base times height.
In this drawing, x times y, right?
Okay.
Okay. Well, there's my area function. That's the one I want to take the first derivative of and set it equal to 0. There's only one problem. It's a function of two variables right now. So I can't do that yet. But since I have this other constraint that I have 2,000 feet of wood, what other equation can I come up with that regards x and y that's independent from this equation?
2x plus 2y is equal to 2,000.
Just 2x plus y. I don't need the other side of that corral. In other words, I don't need a rectangle. I only need three sides of it. I got a building over here that'll keep the cattle in. Okay? Now, this equation here is completely independent from my area equation. And what it does is it allows me to solve for one of the variables. I'm going to solve for y. And then substitute that into my other equation. Now, a is no longer equal to xy. It's equal to x times 2,000 minus 2x. Now I have an area equation that is completely a function of one variable only. Let's solve this. First, multiply them together. In other words, before you can take the derivative of that, you want to multiply them together. Saad, did I lose you or are you still there?
No, I'm still here.
Okay. So multiply x times what's in the parentheses.
200 or 2,000x minus 2x squared.
Now take the first derivative of that.
So 2,000 minus 4x.
Set it equal to 0 and solve for x. What do you get for it?
So 500.
Correct. So my best dimensions are hold on a minute. X is 500. And y is 2,000 minus 2x, so y is 1,000, and this is 500. So my drawing is not quite right. It's more of a rectangle like this. And that's 1,000, and that's 500, and that's 500. So a rectangle, three-sided rectangle where the height is twice what the width is, gives you the maximum area. Notice what the area is. It's 50,000 square feet. But no other configuration here would give me that much area. In other words, if I made it 750 here, 750 here, 500 there, I would only get about 35,000 square feet. To get the maximum area, I want to use this precise configuration. And I got it with calculus. Okay? Now, what was different about this problem, as opposed to the previous problem, is that I had two equations. In the previous problem, the square cardboard problem, notice that my volume function is immediately a function of x all the way around. I don't have another function that I have to solve for y and substitute it. But this is a very, very basic optimization problem. This might be the first one they give you. This is like the definitive optimization problem. And one of the reasons is that it's relatively simple because it's only in one variable the whole way. Whereas the second problem we had, the area was x times y. So we had two variables, but as long as we can relate y to x in some other form, then I can substitute and make this area completely a function of x. And you have to have it as a function of one variable only, otherwise you can't differentiate it. Well, I mean, you could. You've learned implicit differentiation, so when you have two variables you can do it. But for solving optimization problems, you got to get your main function being a function of one variable only. Let's see if I can find another or two. Okay, this gets a little tougher, but here, let's try it. I'm going to give you a different one. I'm going to give you this problem right here. That is y equals negative x squared plus 3. Okay. Here's the problem. What's the largest rectangle I can fit under that parabola? I got choices. It could be that rectangle there, or I could make it a little wider, but that's going to make it a little less deep. Or I could make it a little more narrow. So those are the possibilities of how I can draw a rectangle inside that parabola. Well, what's the biggest rectangle I could fit inside of that? In other words, you can see that there's all kinds of real life problems that this could be kind of useful. Well, we're talking about finding the area of the biggest rectangle. So let's draw a rectangle in there. What's the area of that rectangle?
Base times height.
Okay, what is this measurement from here to here?
Is that 2?
No, it's x.
Oh, I thought you had markings. Never mind. I thought those little lines were markings.
No, it's a big concept, though, that you understand why that's x. In other words, that's that point right there, right?
Yeah.
Coordinates on that point are x, comma, y. So what's the base of my rectangle equal to in terms of x?
2x.
Yeah. What's the height of my rectangle in terms of x and y?
Y.
Correct. So there's the area of my rectangle. again, it's a function of two variables, and I need it to be a function of one variable. Well, I've got y defined, so let's substitute it for that y. So the area as a function of x becomes 2x times minus x squared plus 3. Multiply that out.
Negative 2x cubed plus 6x.
Take the first derivative of it.
Negative 6x squared plus 6.
Set the derivative to 0 and solve.
So plus or minus 1.
That tells us that that point comes at 1 and minus 1. And that's where you would fit the largest area rectangle into that parabola. Okay? Now, let's make it a little bit tougher. Yeah, let me just start. This time, I'm going to draw my parabola like this. And I want to figure out the largest rectangle that I can fit inside of this parabola. And let's call this, I don't care, let's just make it up, x squared plus x. That at least will go through that point there. But it would never go through this point, so let's make it x squared minus x minus 3x. We'll call the parabola that. X squared minus 3x. Well, now the area of my rectangle is still base times height, but base, that dimension right there, how do I find out what that is?
Is it x?
No. What's this dimension right here? That's x. So this distance is x, right?
Yeah.
Okay. What's this distance over here?
X.
This point right here must be 3, 0. In other words, if I plug in 3 here, I get y equals 0. So this actually was a pretty good approximation of this function, except I got it going up instead of down. I know what to do. Make that 3x minus x squared. That's that parabola. In other words, this parabola has zeros at x equals 0 and x equals 3. And so my picture fits. Okay? Now, what's the area equal to of that rectangle?
3 minus 2x.
Good. That's the hard part. Times
Y.
What's y?
3x minus x squared.
Multiply those out. Take the first derivative. Now, one thing you can tell, when I multiply these out, I'm going to have a cubic, right? The biggest degree term is going to come from multiplying that by that. And when you take the first derivative of a cubic, you get a quadratic. And a quadratic always gives you two solutions. So I'm going to get two different values of x when I solve this thing. Well, let's multiply it out first. Let's see, that is 9x minus 3x squared minus 6x squared plus 2x cubed, which is 2x cubed minus 9x squared plus 9x. There is my area function of that rectangle. Take the first derivative.
6x squared minus 18x plus 9.
Set that equal to 0, because that's where your local minimum or you've studied local mins and maxes, right?
Yeah.
In other words, if you have a function that looks like this, that's a local maximum, but it's not a maximum of the function. There's a point over here that's much higher. Okay? Yeah. But it's called a local maximum, and this is called a local minimum because it has points on either side of it that are less. That's all you need to have local maximums and minimums. Well, when you have a cubic function as your area function, cubic functions typically have two local mins and maxes. One's a local maximum, one's a local minimum. Well, we're looking for where this rectangle has the maximum area. Well, let's see. If I solve this, I get 3x minus 3 times 3x minus 3 equals 0, x equals 1. So it's at a value of x equal 1 that the base of that rectangle should begin. Well, that's 1, that's 1, this has to be 1, this point here must be 2, comma 0. And the height at x equal 1 is 2. So the area of that rectangle is 1 times 2, area equals 2, and there's no other value of x that will produce that much area. In other words, if I tried making the rectangle like this, I'm going to get a value, but it won't be as big as 2. Okay? Hence, optimization. In other words, we're trying to figure out how to maximize or sometimes minimize stuff. There's a classic beer can problem. Let's say your Coors or Miller, I'm not a beer drinker, so I don't know even the brands. Let's say you're designing a beer can, and you want to design it for the maximum possible volume given the minimum possible surface area. Right? In other words, I'm making this thing out of aluminum or tin. I want to use as little material as possible to produce a 1-liter beer can or a pint beer can or whatever. I always want to design my beer can so that I get the maximum amount of volume given the least amount of surface area. Well, volume is pretty easy. For a right cylindrical volume is area of the base, pi r squared, times the height. That's the function I want to maximize. Okay? Surface area is equal to what?
I don't remember.
Well, it's a little hard. When you think of the surface area of a can of soup. If you take the label off of the can of soup, you have a rectangle, right?
Yeah.
That's what you end up with if you remove the label from this can that I'm building here. In other words, I'm trying to find out the surface area, the outside surface area of the can. Well, it's the bottom plus the top. That's 2 pi r squared. That's the top of the beer can and the bottom of the beer can, plus the area of this label, the lateral area. Well, notice that the length of this area is going to be the circumference of that can, right? So this is 2 pi r, and this is height. In other words, if I unpeel this can and break it open, I end up with a piece of aluminum that has those dimensions. So surface area is 2 pi r squared, that's both bases, times 2 pi r times h. Okay? So now I have my two equations. Well, I could take this and solve that for h in terms of r. Go over here, substitute whatever I get for h, and then I have volume strictly as a function of r. And if you go through the math of this, you find out that the diameter of the can needs to be exactly the same as the height. In other words, the height of your beer can is twice the radius. And as long as you use that dimension, you will be getting the biggest bang for your buck. If you owned a beer company, that's what you would want to do. If everybody is drinking liter cans of beer, then you want to design your liter can so that it's got the same height as diameter. That way you'll use the minimum amount of aluminum to make a given number of cans. And that's a real key thing, because your profit is what you sell the beer for, or the beer can for, minus the cost of making it. Well, most of the cost of making the can is the material, the aluminum. So you want to minimize that while maximizing volume. Or you might want to minimize this equation given a certain volume. The way this problem typically comes down is the volume, say, has to be 1 liter. And now what you're minimizing is that equation. Given, in other words, this is a little similar to the farmer with the barn and the corral. He had a certain amount of wood, and he wanted to build the biggest area he could with that amount of wood. Well, here we know we want a 1 liter can. It has to hold 1 liter. How do I minimize the amount of material used? Well, I can now solve for h in terms of r. Go over here, substitute it, take the first derivative, and solve for r. And what the radius has to be. And the radius will turn out to be half of the height. And that's another kind of a classic optimization problem, similar to the farm and the corral. And these optimization problems, they cover such a wide range of topics, it's unbelievable. And optimization might be the reason that calculus is called the greatest math discovery ever. More than trig, more than geometry, more than any of the others. It allows us to determine stuff in the real world that we never used to be able to figure out because of calculus. Because of this one principle, that if we have a function and we take its first derivative and set it equal to 0, we will know where the maximums or the minimums of that original function are. If I give you this function, and I want to know that point and that point, then all I have to know is that function. Let's say that function is x cubed minus x. If I take the derivative of that, set it equal to 0, I'm going to come up with two different values for x. That's going to be one of them. That's going to be the other. Now, perhaps you've realized by now that it's not always a maximum that we find. In other words, y prime here is 3x squared minus 1. So I get x is plus or minus the square root of 1/3. Well, there's one of them, there's the other one. One is a maximum, the other is a minimum, and we don't know right off the bat which is which. Okay? So the way I determine which is which is I take the second derivative. What's the second derivative of this function? Okay. What do we know about second derivatives? Now, if I plug in my two values of x that I came up with, one of them gives me a positive second derivative, the other gives me a negative second derivative. What do I know is true if the second derivative is positive? Is the function concave up or concave down?
Concave up.
So, if my second derivative is positive, I have found the minimum. If the second derivative is negative, I have found the maximum. Just by taking the first derivative and setting it equal to 0 doesn't do that. It merely gives you the two spots on the original function where you have a horizontal tangent line. But a horizontal tangent line comes where we have local maximums and local minimums. So you have to apply the second derivative test to determine which is which. Now, sometimes the second derivative test won't answer the question. You'll do the second derivative test and it'll come out to be 0. So then you have to do what is called the first derivative test. You look at your 2 points you came up with, this one and this one, and you look to the left and you figure out what the slope is to the left of that point. Well, these slopes are all positive. I come up here, I get my 0 slope. Coming down the other side, it's negative. So if my slopes go from positive to negative, it's a maximum. If my slopes go from negative to positive, it's a minimum. And that's the first derivative test to tell you whether you have a minimum or a maximum. Now, that test requires you to go into that function and plug in values less than square root of 1/3 and then greater than a square root of 1/3 to determine what your slopes are doing here. Well, that's a lot of math. So, to me, the second derivative test is by far the easiest one. It's really easy, usually, to take the second derivative, and once you've taken it, plugging in the values you got for x, it's real easy to determine what makes this positive and what makes it negative. And just know that positive second derivatives mean maximums. Negative second derivative, that's the other way around. Positive second derivative means concave up. So a positive second derivative means a minimum. A negative second derivative means a maximum. And that's how you tell the difference. And the other thing is the second derivative, wherever it's equal to 0, is the inflection point, which is the point between concavity. There's also an inflection point over here the way I drew it, because everywhere here is concave up, everywhere there is concave down until I hit this inflection point, and then I go concave up again. Okay, so whenever you switch concavity, the point at which you switch it is the inflection point. And typically, the inflection point is where the second derivative is equal to 0. And that's stuff you've been learning already. In other words, that's what your test probably had a lot of. All right. That's a good place to stop. I'm sure that by next Friday, you'll probably have a number of optimization problems to give me. And we can work on them. I mean, if you don't, I have more. But they're pretty cool. At this point, it's the most useful use of differential calculus that you have found. Being able to optimize a function. Without calculus, you give me this function and I don't know where the maximum is. I would have to use a lot of trial and error, or I'd have to graph it and I would have to put trace on there and find the maximum. But I would have no algebraic way of calculating without calculus. All right, Saad, I will talk to you next Friday. Same time.
See you.
Bye-bye.